Introducing Laser Tag.
I'm Nathan.
I'm Ian.
I'm Chris.
I'm Josh. We're going to give you a quick demo of our laser tag project.
So when we pull the trigger, the gun emits an IR signal. We generate this signal using an IR LED like this, and then we focus it through a lens like this one right here in order to narrow the signal and make sure it's very strong so that you have to be accurate with your shots and you have longer range on your gun. So this signal is received by IR receivers like this one right here, and from there we can decode the data within that signal. We decided to use the RC5 communication protocol to encode data within our signals. This is typically used for things like TV remotes, and this allows us to send unique packets for each vest so that when we receive a packet from wherever, we know exactly who shot us.
So, having 3 separate smart fusions in our project, we needed a way to communicate between them. So we decided to use the NRF24LO1 2.4 GHz wireless transceiver. So one of these modules is housed in each of the 2 vests and the central scoreboard. So we created our own packet to use this. It contains the sender ID, the receiver ID, the command type, and then the data for the command. So typically what we would do is if a player fires and hits another player, this player will register which of the nodes was hit, then it'll transmit a packet to the scoreboard saying player 1 has been hit, and the scoreboard will say, okay, update score of player 2 by 75, and then it'll transmit player 2 updated score to player 2, which will then update the LCD on its blaster.
So this is the central hub for our project. It's its own smart fusion, and it basically controls all the game mechanics and drives the scoreboard. This scoreboard is custom VGA that we're using sprites to display everything on the screen. Now, the Smart Fusion has limited memory space, and it also has a limited number of logic tiles, so there's only so much you can do. For example, I have the capability to display 16 sprites in memory, but I don't have the logic to actually compute which sprite is in every location. So you have to make trade-offs about how many sprites you can have and where they can be on the screen. In our case, we're allowed to have 8 sprites. Each one is roughly 16 by 24 pixels, and they can all be scaled up to a factor of 8 times the original size. This allows us to have lots of different images at different sizes in lots of different colors. We have the full 8-bit color code, and these are easily configurable from software. So I was able to debug this design and change the look as I was preparing for the expo.
So, as an additional source of player feedback, we decided to add small LCDs on each of our blasters. So this is a 1.44-inch SPY-controlled TFT LCD that we got from Adafruit. We communicated over the SPY bus, so we had to adapt a library and make it into a custom version. It involved porting it from C++ into C and changing some of the SPY functions, and then adding our own graphics. So we created a background and then a score update, so it tells the team name and the score, and additionally there's a player indication when the player wins or loses.
To provide more feedback to the user, we've included an MP3 player on our gun. Inside this 3D printed box is not only the MP3 player, but the board used to control the MP3 player. This board is the DF Player Mini, and what we do is we insert an SD card with all the MP3 files we want to play, and we can communicate to this board over UART, telling it which file we want to play. When the player pulls a trigger, you'll hear a shoot sound, and when the player gets hit, you'll hear an alarm sound.
So, in order to add another source of player feedback and make the game more realistic, we added haptic vibration motors, like the kind you'd find in a cell phone, to our vests. So there are 2 in each shoulder. As you can see, there's one here, and there's also another one over here. So whenever a player gets hit, the motors will vibrate to let the player know that they've been hit.
So here's a close-up of the PCB we used as our haptic motor controller. It essentially consists of a transistor and a diode for protection for the motor. We decided to add this board so that the haptics would be more compact on our vests and they wouldn't feel bulky when the player is moving. This motor controller is needed because otherwise the motors would have to be powered directly off of the GPIO pins, which can't provide enough current to power each of the motors on our vests individually.
To make our game more engaging, we wanted to include these individually addressable RGB LEDs. We communicate to these LEDs over pseudo-SPI, but one of the biggest problems is that, just like a strand of holiday lights, if you break one of the LEDs, the rest of the lights in the strand fail. So you can see that problem actually got demonstrated here, where these lights are the first in the chain and they work, but the blaster lights are last in the chain and they're broken.